So, hey everyone. That's my first DEF CON actually. So, smile. Okay, so today I'm going to present to you a research that we have done last year on Qualcomm drivers code for Android. So, our agenda for today, first we'll briefly speak about chipsets, their location in the Android ecosystem, how they affect the overall security of Android. Then we'll focus on Qualcomm as a chipset and review its various subsystems. Afterwards, we will reveal 4 new ODA vulnerabilities that we have recently discovered, including a fully working exploit for one of them. Finally, we will discuss some ideas for improving the overall security of Android. So just a little bit about myself. My name is Adam Donenfeld. I've been a security researcher for years, both in the mobile and in the PC field. I've mainly done vulnerability assessment and exploitation. Right now, I work at Checkpoint as the lead security researcher for Android, and in my free time, I also study German. Additionally, I would like to thank Avi Bashan, Daniel Brady, and Pavel Berengold for supporting me during the research. Okay, so most people think that only Google is involved in the development of Android, but that's not the case. Many other third-party vendors take a large part in the final product we buy. The heart of every Android is obviously the Linux kernel. Afterwards, we have the AOSP, Android open source project, which is developed exclusively by Google. And then things start to get a little bit more complicated, because then we have the chipset. So what is actually the chipset? So when you buy an LG, HTC, Nexus, or Samsung device, even though these companies do manufacture some of the hardware, the majority of the hardware is actually manufactured by the chipset vendor. Now, not only the hardware is manufactured by the chipset vendor, but the drivers for this hardware is also a role of the vendor. Then this entire package is forwarded to the OEMs and is modified by each OEM and receives various customizations. And then finally, we get our device. Now, as you can see, chipset is very essential in this process. And if you find a vulnerability in the chipset code, it means that it has to go through the entire, all the OEMs. So it does not only mean a long wait and fix, but also a very large victim pool to attack. So if we find a vulnerability in Qualcomm, we're posting this to all Nexus, HTC, LG, and many Samsung devices. So Qualcomm has a very large impact on the overall system. In fact, there are a lot of different subsystems which are completely written by Qualcomm. Each one of these subsystems is a great place to start to look for vulnerabilities. And if the component is low level enough in the system, one vulnerability would probably be enough to completely compromise the system. And that's without mentioning components that have been modified by Qualcomm to satisfy its requirements. And we will see an example soon. So today, I will be disclosing 4 new ODA vulnerabilities, each one of them accessible for any unprivileged application on the device. The first one is Ashmanian Devil. The second one is Koala Root, which we already exploited. The third vulnerability is called Sincoca Root, and the last one is Kangaroo. So let's start with Ashmanian Devil. So Ashmanian Devil is a vulnerability in the ASHMEM mechanism. ASHMEM, or Android shared memory, is a unique shared memory allocator for Android. It reminds a little bit the Linux SAGM mechanism, but with a slightly different behavior, and it supports a very simple file-based API. Now, Qualcomm expanded the functionality of ASHMEM, the API of ASHMEM, so it can easily obtain an information about a file, an ASHMEM file from an FD. So for example, we use it if you want to map ASHMEM memory to the GPU. So Qualcomm added this function. So basically, what the function does is it gets a file descriptor, and a few output pointers. It extracts from the file descriptor the internal kernel structure of the file. It checks that this file is actually an hashmem file, and if it is, it extracts data from the file. If it's not, the ref count is dropped back, and the function is finished. So it's kind of straightforward, and in fact, we couldn't find a vulnerability there. But a question that most of us must ask ourselves is, how does Qualcomm actually verify that our file descriptor is an hashmem file descriptor? So the way to do that in Linux is first to extract from the file descriptor the internal structure of the file, which we can see here. Just a second. Which we can see here. And then each file in the system, let's take, for example, a socket file. Each socket in the system has a file. So there are a lot of file types in the system. So in order to determine their type, each file has its a specific operation handler. For example, let's say that we perform a write operation on a socket file. The behavior in comparison to a regular file is obviously different. So we simply have to check the handler of the specific operation, and then we know the type of the file. So Qualcomm decided to reinvent the wheel, and the way that they checked for a type file was by the name of the file. Yeah. If the file is called hashmem, it must be an hashmem file, right? So what we got here? If we have a file called hashmem on a root of any mounting point, we can fake the internal hashmem data. But unfortunately, slash is read-only, and any mounting point on the system that is inaccessible for unprivileged applications. And we said that we want to exploit it without any prior permissions. So what we did to overcome that was using a feature called OBB. So OBB, or OPQ binary blobs, is a deprecated feature that fortunately still works. So as you might know, Google Play doesn't allow apps with file size that is greater than 100 megabytes. Now, obviously, there are some apps, especially games, that have lots of sounds, structure, textures, pictures, whatever, and they cross the 100 megabyte limitation. So what I usually do is first downloading just the core functionality, and then they download externally and the rest of the textures. So what OBB is basically a file system that any app can download and mount. And so let's say that let's take Angry Birds, for example, of a game. The first time we launch Angry Birds, it downloads externally all the pictures and the sounds. And then it downloads an OBB file and it mounts it. So any developer can create an OBB file and put there any file he wants, externally download it, and then just mount it on a device. So in order to fake an hashmem file, what we can do is first just create an OBB file and put the file called hashmem in the root directory. Then we can just mount the OBB, and then we can send our file descriptor to the hashmem file from the OBB to the system, and therefore we can fake the hashmem internal data. Thank you. Okay, so now going to the second vulnerability, koala root. So koala root is a vulnerability in the IPC mechanism of Qualcomm. It's basically a new address family in the system, AF MSM IPC. But it has some unique features. For example, I can whitelist or blacklist other sockets in the system and filter them by the group ID or other properties. And therefore, I can prevent unprivileged processes from communicating with me. And now, another cool feature in this IPC, anyone can monitor the entire system. So, for example, I can get a notification for any creation or destruction of a socket with this address family. And the best thing about it, no permissions are required to do that. So this address family has 4 different subtypes. We are going to focus only on client port and control port, mainly because IRSC port and server port require high privileges. So every time you create a socket, the socket is a client port socket. A client port socket can communicate with other endpoints and send and receive data. Now, control port is a socket that cannot communicate with other endpoints. It will only receive messages about the creation or destruction of sockets in this address family. So how do we create a control port? We simply issue an ioctl on the client port. So the function that handles the ioctl is this one. Basically, it locks our current endpoint, so we can't issue 2 ioctls simultaneously on the same socket. And then, according to our command, it performs operations. So if we issue IPC router ioctl bind control port, it will be converted from a client port to a control port. So that's the function that converts our socket. So each type has a list, and the conversion is simply taking out a client port from its list and putting it back into putting it into the control port list. So that's the conversion function, and there is a vulnerability here. So let's examine this function step by step and find the vulnerable code. So can you see the code here? Is it visible? Okay. So the first instruction is taking a lock on the client list. That's because we modified the list. And then we take the object out of from his list. Then we unlock the client list. We lock the control list. We add our object to the control list, and then we unlock the control list. So let's examine it. Locking the client list, taking the object out from his list, unlocking the client list, locking the control list, adding our object there, and then unlocking the control list. Pretty straightforward, and in this flow, nothing was problematic. But what happens if we try to convert an object that we have already converted before? So we lock the client list. We take the object out from his list, which is not the client list. We unlock the client list. We lock the control list. We put the object back, and we are unlocking the control list. So for those of you who missed, even though we take a lock on the client list, we are modifying without locking. We modify the control list. So we got something here. The control ports list is modified without a lock, and therefore there is a race condition. We can delete 2 objects simultaneously from the control ports list. Okay, so now, just a second, sorry. Let's see what happens when we delete 2 objects simultaneously from the list. We're working in the context of A. That's the Linux kernel code that removes objects from a double-linked list. And if you can see it, so you have the pseudocode here. So basically, we are taking now A is next, which is B, and we set B's pref to be A's pref. So B's pref equals control ports. And now, since the list is not locked, there might be a context switch. So now we're working on the context of B. So we take B's next, which is C, and we set C's pref to be B's pref. So C's pref equals control ports. And now we have to take care of B's pref, which is control ports. The second, yeah, now take care here. Sorry. So we set control ports next to be B's next. So control ports next equals C. And finally, B now points to poison and is removed from the list. And it's not just removed from the list, but it is also freed. So now this memory is reclaimable by kernel heap spraying or any other method you choose. And now, going back to A, we take care of A's pref. So control ports next equals B. And just like B, A is removed from the list, it will now point to poison, and that's it. So if we remove all the unused objects in this list, you get this. So the list now points to a free reclaimable by kernel heap spraying data. So we just use Unix diagrams to spray that. Now, since this is the list of the control ports, now once we fake an object there, we want the list to be used. So we just create or destroy any endpoint in this address family. And each time we do that, all the objects on this list must be notified about that. So the notifying function is post packet to port. So each object in the control ports list is transferred to the post packet to port function. So that's the function. We're not going to go all over it. But as you can see here, we have a lot of new primitives, from information disclosure to function calls, memory corruption, and many other primitives. I think that there is at least one more way to exploit the vulnerability, but the path that we chose was using wake up. So what is wake up? Wake up is actually a macro to another function called wake up common. As you can see here, since we control the first parameter of wake up, we also control queue. Now, task list is derived from queue, so therefore we control cur. So we have a new primitive here. We can call any kernel function we can call any kernel function while we control a large portion of the first parameter. Now, if we wouldn't have smap, it would be a game over, but we want to overcome smap. So a new primitive, kernel function call with the first parameter controllable. However, it's not good enough for commit creds. Commit creds, for those of you who don't know, is a kernel function that allows you to change your current credentials. Now, since we control most but not all of the first parameter, we can't call commit creds because we want full capabilities. That's because the kernel address is a part of the first parameter. So if you want to control the accurate kernel address, we cannot control 100% of the first parameter. So we had to upgrade our primitive. We have to find a function that controlling just a little bit of its first parameter will allow us to call another function with 100% control over its parameters. So we looked for such a function, and we got USB read done work fn. As you can see here, we control work, so we control ch. Controlling ch allows us to control rec, and therefore we can call any function while we have 100% control of the first parameter. So buff is an address, so we can just put any pointer here. And so each time we want to call a kernel function now, we have to go through over this chain. So first we call wake up common, which you can see here. Then we call, using this function, we call USB read done work fn. And finally, we can call any kernel function and while controlling the first parameter. And now we have enough primitives to completely compromise the system, get ourselves root, disable SELinux, and clean up our mess. So let's start again, the exploitation flow. We have a list, a double linked list, and each time we create or destroy an endpoint on the list is iterated, and it will be used. So the first thing that we want to do is get the use after free situation that we saw before using the vulnerability, and therefore put a fake object there. So first there is a free object in the list. Now, since this memory is reclaimable, we can just use heap spraying to reclaim this data. We used Unix diagrams, but again, you can choose your convenient spraying method. And now we control this object. Control this object. And the next thing we want to do is get the system to use this object. So trigger an iteration on the list. So we just close or create any socket on this endpoint. Our object is being used. And then we go to the function chain call. We go to wake up common. which uses our fake task list, and then we can call kernel functions conveniently. So the first function that we call is qdisklistdel. It cleans up the list, so our fake object will no longer be there. In fact, the list will be just empty. So for the use of the list, nothing will crash. Then we call enforcing setup, which effectively sets SELinux to be permissive. And finally, we call commit creds, which sets our UID to 0 and gives us the full available capabilities available to the system. And we won. Thanks. And now, time for a demo. So on the left, we have a console. I hope you can see it, but you really have to believe me. First, we install our demo app. And we are going to see that this device is a Marshmallow device with a relatively new Linux kernel version. Now, additionally, we're going to see that SELinux is fully enforced and that SuperSUSE is not installed on the device, so it's not rooted. It actually comes like from the store like that. And we're going to see that we are not root, so we are running on the user 2000, so shell. Okay, now our payload put a SOID file in the system partition, and it creates a service, a local netcat server listening on port 1337, which just forwards commands to bash sroot. So now we're going to see that system is not modified and that this local server does not exist. Okay, and now we're going to launch our exploit. So we're going to see some crap on logcat. Be patient. That's it, we're root. So now it just cleans up stuff. It takes approximately 2 seconds to exploit this vulnerability, and then you can run your own payload as root without nothing that stands on your way. So now we are going to see that we are still not root. You don't have a SU, and we are not root yet. But SELinux is now no longer enforcing; it's permissive. And if we try to netcat to our local server, instead of getting connection refused, we are in. So now we see that system has a new file called zugang that's accessed in German. I'm studying German. And we're going to see now fstab, which is only accessible to root. So, and finally, ID shows that we run as the kernel, and boy my returns root. Thank you. So that was qualroot. And now we are going to the last two vulnerabilities, syncockaroot and kangaroot. But before we talk about them, we have to talk a little bit about a mechanism called IDR. So IDR is a Linux kernel mechanism, so it's not just for Android, and it allows mapping between numbers, like just IDs, to kernel pointers. When do you use that? Let's say that we want to let the user reference kernel object, so we don't want to reveal the kernel address of this object, so we just give them a safe ID. So how does it look? The user wants to create an object, so it sends the kernel a create object request. Now the kernel allocates data and initializes a new object. Now the kernel doesn't want to give back this address to the user. So instead of doing this, it just passes this address to the IDR mechanism, which now maps between this address and the number 1. And now the number 1 is returned to the user. And each time the user wants to update the object, destroy the object, do whatever it wants to do the object. It will send the kernel just, hey, I want to update this object ID 1, and the kernel will use the IDR mechanism to get the address from this one. And now, syncocca root. So syncocca root is a vulnerability in an object called sync source. It's in the synchronization mechanism between the GPU and the currently running application. We don't have to know a lot about this object to understand and see the vulnerability. We just have to see how to create and destroy this object. And as you've seen before, the IDR mechanism, this object is referenced with the IDR mechanism. So that's the function that frees the object. The user controls data. I mean, it is sanitized, so actually it just controls ID here. And KGSL sync source obtains from this ID, this IDR ID, a kernel object called sync source. Now, how does it work here? It's a ref count-based object. So first, the ref count is 1. Once we called this function, the ref count is increased to 2. Then it is dropped once for the creation of the object because it's the destroying function. And it is called once again because we increase the ref count here. So at this point, the object is freed. But something is missing here. Is there any pending free check on the object? What happens if we call this function on 2 different threads simultaneously? So let's examine it. We have thread A and thread B. Thread A called the destroying function. So now the ref count is 2. Now it drops the ref count to 1. And then there might be a context switch. So thread B now calls the destroy function. Now the ref count is going again to 2, but immediately they dropped back to 1. Then we are going back to thread A, which drops the ref count to 0. And on this point, the object is freed, reclaimable, and any kernel heap spraying will catch it. And finally, since thread B did not finish the destroy sequence, the ref count will be dropped to a -1. And on this point, once the ref count is 0, we can cause another object, our malicious fake object, to be freed. And then we can further it. So again, the POC, we are creating an object and a sync source object. And we create 2 threads which use the destroy function on the object simultaneously. The ref count will be dropped to -1. Before it gets to -1, it's on 0, and then we can heap spray the kernel, catch it, and we have a double free, which leads to use after free. So that was in Cockroot. Now, finally, Kangaroot. So Kangaroot is a vulnerability in the KGSL -3D0 mechanism. It's the wrapper between the user mode and the GPU. So each time we map data to the GPU, another object called KGSL mem entry is allocated, and this object manages the address range, the range that is mapped, how many object, like a ref count, protection level, and many other properties. And again, if you want to unmap this data, we can use the IDR mechanism because the mappings are used by the IDR mechanism. So the first thing that we did was going to the destroy function. And we saw this, which looked pretty cool because there was also no pending check on the destroy sequence. And then we went to shared mem free entry. And for some reason, unfortunately, they didn't forget to do that here, so it's appropriately locked. So we don't have the same vulnerability again. So in frustration, we went to the creating object. So this function gets, I told you, KGSL mem entry. So it just gets blob of data. It associates this data with an IDR, with an ID using the IDR mechanism, and then it initializes the data. It maps it to the GPU, and it adds it to some lists. So that's not appropriately locked. Why? Because once we associate it with an IDR number, it is already we can already reference it from the user mode. So here is how we use this object. Thread A creates some, it allocates some data. It's already, everything here is, by the way, in the kernel already. So thread A allocates data. It associates the data with an IDR number, so anyone can reference it now, and then it initializes the data. Then thread B, it checks for if the IDR item exists, and since it is, it passes this check and frees the data. But what happens? What happens if thread A allocates data, associates it with an IDR number, and right then, thread B issues a free request on this object. The object is already there, so we pass the if check, and then the object is freed. So even though the object is freed and reclaimable again by kernel heap spraying, thread A did not finish yet. So now free unused data, which can be used by us, will be initialized, and we have another use after free. So again, the POC, first we map data to the GPU. We get a number. We are going to know which number will be next, because as you can see here, it is always increased by 1. And then we issue simultaneously a create request and a free request on another thread. And there might be, again, a use of the free in the function kgsl mem entry attach process on the entry parameter. So that's a POC. Now, disclosure. So obviously, we disclose everything. We had a collaboration both with Google and with Qualcomm, and I must say that Qualcomm was very responsive. They were very collaborative. So Syncocca root was fixed on the 6th of July. A patch was released, and Google deployed it to the Nexus devices on the 6th of July also. Kanga root was also fixed on the 6th of July, but for some reason it was only fixed the patch was only deployed on the 1st of August. Ashmani and Devil, I'm sorry to disappoint you. Even though Qualcomm released a patch, no device was fixed so far, at least no OEM that we know about, so you're all vulnerable. Congratulations. And finally, Qual root. So Qual root was the first vulnerability that we disclosed, and even though Qualcomm released a patch back in April, Google did not deploy it yet. And I would like to talk about Google for 1 minute. So, despite the average bug report, which usually contains a document and 5 lines of code in the best case, we supply them with a fully working exploit for any Qualcomm-based device. And they classified Qual root as a low severity vulnerability. Now, what the hell? I mean, we sent an exploit. So we approached Google and we asked them why they classified our vulnerability as a low severity vulnerability. And you know what they said? They said that they planned to block this mechanism using an SELinux rule in the future. So we sent it to them. It was vulnerable on all the devices, and yet they said, yeah, in the future we'll fix that. So it's just a matter of timing, sorry. So maybe I hope that it will be different for the next time. And this is just a single example. I mean, that's like that's a proof that it's possible. We might have out there low severity vulnerabilities which are exploitable, and it poses a very high risk on all our Android devices. So, suggestions for the future. And I'm not going to say pay more attention to your code, because it will never. That's not a practical suggestion. I'm going to give you concrete suggestions. So the first one, For more than a decade, commit credits was an extremely convenient function for exploiters. I mean, back in 2008, people did that. So maybe we can somehow harden it. Let's take Cisco Reboot, for example. It actually receives magics. So you can't call Cisco Reboot by mistake. So maybe we can harden it, make it inline, put magics, but this function cannot be in the kernel anymore. Not in this current situation. Now, my second advice, KASLR. So ASLR is not a new concept. iPhones are also running ARM, and they have it for years. New Linux kernels do support ASLR, and yet for some reason, Android users don't enjoy from this benefit. So I really think that KASLR for Android should be prioritized. Without KASLR, it would be much more complicated to exploit Qualcomm and I think every other kernel vulnerability. The last advice. So SELinux is a really great security mechanism, and it greatly decreased the attack surface. But still, I don't think that unprivileged applications should have access to Qualcomm's internal IPC. And even though it's nice to have it, but we should pay more attention to the rules that we deploy there. Now, with that said, the overall status of Android is fairly good. SMAP, or PXN for ARM, which was introduced last year, made everything much more complicated, and yet a few small components are missing to make everything much more safe. Now, we created an app which should be published like now. So it is called Quadroot Scanner. You can check. Using this app, you can check if your device is vulnerable. Now, for Ashmani and Devil, it must be, but for the rest of them, you might be surprised if it's like that or not, if it's vulnerable. So it is also searchable on the Google Play, just Quadroot Scanner. So thank you very much. I hope you enjoyed the presentation. And so we have like how much time? Like we have like, so we have like 5-10 minutes for Q&A. So if you have a question, just queue in front of the microphone and ask.
How many devices you think are affected by these vulnerabilities?
So the question was how many devices are affected by this vulnerability, by these vulnerabilities. So a few hundreds of millions, I think about 700, 800 millions, more or less. No, small number.
Hey, awesome work. I was wondering if you've looked into any of the Qualcomm OSs like the Radio OS, RPMB, or touched any of the non-Linux stuff.
Can you repeat? I couldn't hear you very well.
Hey, I'm wondering if you've looked into any of the Qualcomm other OSs that run on a device, the non-Linux OSs like RPMB, TZ, or any of the non-Linux stuff that's running.
Okay. Yeah, we weren't sure about it, but since, for example, the Android wearables like the watch, since they also use the same, okay, at least for Qualcomm, since it's not ARC-based, just logical code, I mean, not logical, but it's not based on the CPU, we do believe that it might be vulnerable. We did not check that, though. So we're welcome to do that. Yeah.
Hi. On the demonstration, I noticed the security patch string was from October of 2015. Is there a reason you didn't demonstrate against the latest version?
Not really. We discovered it back in like January, and that's the device, January, February. So that's the device. That's like, we just took it from this date. But there is no reason for that. I mean, on the latest versions, Google did deploy a SELinux rule that blocks access to the Qualcomm IPC, but you can just, you can, I mean, if you disable SELinux, so it's exploitable and it is indeed vulnerable. I mean, devices did not receive a patch yet.
Did you get trust zone access at all through?
Okay, so once you're root, you have access to the trust zone mechanism. This vulnerability is, however, in the unsecure kernel context, and therefore it does not give you access to the trust zone kernel. However, you can exploit previously disclosed vulnerabilities to achieve the code execution in the trust zone level, as seen on other research on the internet.
Cool, cheers.
Other questions? Thank you.